Hello.
Yeah, good afternoon.
Yeah, good afternoon, all. Uh, so, okay, so yesterday we have discussed and I hope that session was fruitful to everyone. So, basically, I have oriented the first session, inauguration session, just like very basic and fundamental so that every faculty can be rooted through the where it comes from. So now we will move ahead from that PPT and we'll continue the things. So let me share. So okay. So, yeah. So we have discussed about more very much about quantum computing, where it comes from, what are the things, what are the discreteness and continuation. Uh, so there is a very much need of the nature. So that was the last slide we have left. So yeah, Feynman has triggered this concept, and the IF emphasizes a lot in this fact that we are not compelled by our requirements of shifting from classical to quantum. Well, that was a requirement that is okay, but this was not the compulsion. Actually, the original question of the Feynman was that the nature is quantum. So when the nature is quantum, so we should develop this earlier. Okay, so that was the demand of the nature. So that's why we have moved towards the quantum computation. So all these questions we have discussed. So yeah, so we did not choose quantum computing. This was the statement in that time. A lot of scientists in the 90s. So we did not choose quantum computing. The nature forced it. And the universe never computed in bits. As I described in the last round, that nature always prefer the continuity. So the nature never prefers in the bits. It always computed in the qubits. Okay, so qubit will form the continuity nature. So the quantum is not ultimately, we will say this, futuristic, the quantum is fundamental. This is the inherent property. We should continue this. We should not develop the quantum computation or the classical computation. It's only meaning that directly. So the sequence was wrong, but the things right now. So we now, so we are coming to the math behind the qubits. So there are some fundamental things as we have spoken that this quantum computation has arises from interdisciplinary field. We have and this interdisciplinary field, some of the concepts, the basic concepts we have taken from the physics that we have discussed. Now, uh, from the math point of view, because we can say mathematics is the language of every subject, right? So whether it is a physics, chemistry, or anything else, biology, whatever, mathematics has to be there to speak about something. How we can speak about and data or something. So that to represent that data, to represent that things, the statistical things, and we need a mathematics. So this is a language of everything. But now, beyond that language definition, it tells about some more because this math is the thing which forms the logic behind these things. Okay, so the logic we are talking about in physics converted through this mathematics. So we have to read it. So the in the mathematics, so some concepts of the vector space we required here, the Hilbert space we required here, and the most fundamental is if you can skip the vector in Hilbert, but the most fundamental, the matrix concept. This matrix concept we require as a operator. So if somebody is not the mathematics background, although it often it occurs often very less because everybody is having the mathematics background, but need to be revised these things. It is not a bit typical mathematics. It's a typical simply a linear algebra we can call it. So that linear algebra covering only a 6 to 8 in the standard math and some of the matrix concept of the 11 standard, right? So this vector Hilbert matrix and a linear combinations. So it is a linear algebra, so we have to make a linear combinations and some of the inner and outer products of the mathematics. So these are the fundamental ones. So we will discuss a very little bit about these things so that we can form qubit definition. So, first of all, I will discuss about this. Actually, this vector space, Hilbert space, these are the very heavy gravity terms coming from directly. So, without knowing the exact background of the mathematics. So, this Hilbert space and vector space, these are the topics of the gravitation side. So, if they are coming in abruptly in the BTech courses, so naturally the student will surprise the what are this Hilbert space and vector space. So, you need to be clear to the students that these are the nothing. These are only and only mathematical structures that we have to take in the definitions of this. So what are that? So space defining the worlds are something which collect uh, the elements. Elements means anything it can collect. So if we are talking about the element, that means element may be a sport person. Elements maybe of suppose if we are talking about a kitchen space, then in the kitchen space, the elements which is forming the product of that space. So if we are talking about the kitchen space, then the products in the kitchen we are making, just like an example, I can take it tea. So tea we are taking as a product, food we are taking as a product. So in the kitchen space, if we will talk about the kitchen space, suppose tea is a product and food is a product. So, what are the elements of this tea? So, these tea elements are milk, these tea elements are this sugar, these tea elements are tea leaves, or basically tea, we are calling it. These are the elements. Yeah, of course, water is there. Of course, water is there. Okay. So suppose we are talking about the kitchen space. So knowingly, I'm taking this example. In the kitchen space, we are taking the components of that product which they are making. They are making tea and foods. So I'm taking the these water, milk, sugar, and these tea. All these four are the components of the kitchen space. So we can take, so the element of the kitchen space are these four are the elements belonging to the kitchen space. So if we are talking about the food, food is another product, and in the food there are some spices, there are some raw material like rice or flour, which we are calling atta in the Hindi, and there are some more materials like vegetable. Okay, so all these things are called elements of the this space, we on from which this product is being made, right? So from that example, I hope you will clear the students that vector spaces and Hilbert spaces are nothing special spaces. So the ultimate aim is to realize the students to that whatever we are reading, that is coming from our daily life examples. It's nothing new. So Hilbert space, somebody will shake their roots when he will hear Hilbert space. It's a very high gravity spaces, words we are used to hear. Okay, so the students are need to be tackled through a daily life examples which they are moving around, right? So so like that kitchen spaces. Yeah, when we are talking about the elements, so these element ultimately, when we are talking about water, milk, this sugar and all these things, ultimately these element is having some basic rule to have the product. So basic rule is that it is having in some proportional, like suppose whatever I'm taking abstract examples, 1:2 into 3:1, like that. These are the proportions. So these proportions are called the rule of this vectors. So we will call the rules, these proportions are the rules. They are bounded by this rule. That this rule governing the kitchen space, these four elements. Okay. So that means if we will talk about the vector space, so in the vector space also, there must be some elements. That element must have some rule, and they are governing by, which is that should be governed by vector space, right? As here, the rules of these four elements are governing by the kitchen space, right? So if we will talk about another example for this, so let me clear the drawings. Yeah, another example, if we will talk about, suppose drawing room space, okay. So in the drawing room space, what are the key things? The key things I think in the drawing room space, everyone should have a permanent sofa, right? In the drawing room space. Another key component in the drawing room space, we are having a TV. Another key component, we are having a chairs. Or all of you can suppose that arts, crafts, these are the fascinating things we have to hang over the walls like that. The all that things we will call it as a vector. But what vector? Vector which is belonging to the drawing room space. So this is drawing room space, right? So all these things, this is one vector, this is second vector, this is third vector. If we will call it craft and all that, that will be a fourth vector. Say all these vectors should have something relation in between each other. So that relation means only you can have a two sofas in the drawing room, or you can have only one TV in the drawing room like that. So there must be a these elements must follow some rules regarding that space. So that rules governing the drawing room space. So what the drawing room space? What definition it is bounding? So this definition is bounding the quantity of the sofa, is bounding the quantity of the TV. So that means from these two examples, I hope so you will be able to clear the students more friendly way that we are having all these vector spaces in all around our daily life examples, right? So, so the elements. So now, if we will return to the our vector space, take some elements. Some of the elements we have to take it, and these elements, suppose A, B, C, these elements we have to take, and these element is bounded by some rule, and that rule we are governing here. That rule we are governing here because drawing room definition itself governing the rules. The kitchen space definition itself governing the rules. Now, another rule in the kitchen space, I can quote the example. Another rule for the kitchen space, that must be non-toxic. Now, whatever the elements of the kitchen, that must be a non-toxic. So that also we can implement that rule in the kitchen space. So here, just like that, in the vector space, we can make a rule. So what the two rules we are making here? So we want to utilize these two rules. That is, one is inner product and other one is outer product. So vectors are bounded by the inner products and outer products in the vector space. Okay. So, what are the inner products? Inner product is nothing. If we will talk about the mathematics language, when we will talk about the mathematics language, so inner product is nothing. Inner product are simply called a dot product. We know that there is a dot and cross products, right? So the inner product are simply called the dot products. And the outer product, that is simply called a tensor product, are simply called the tensor product. Okay. So the elements of the vector space, they are governing by the two rules. They are bounded by the two rules, that what inner product and outer products rules, right? So this inner product, that is nothing, only a dot product. Outer product, that is nothing, only the tensor product. So knowingly, I'm not going in that same definitions. What I think, I hope all of you are dealing with the quantum. So all of you are explaining the students that these like these things, and why we are taking inner product, why we are taking outer products, what are the inner outer products. So I think you must be elaborating all that things. Okay. So what I'm feeling here, what are the things required to accelerate your teachings, that I'm only giving here. So, and that is the ultimate of aim of this FDP also, to accelerate in that direction. And it doesn't means that whatever I'm telling here, it doesn't means maybe most of you have used these things, these examples in your teaching, or maybe not. So if used, then okay, no worry. If not, then you can take the advantage for this. Yeah, so now we are talking about now Hilbert space. So Hilbert space is the main space which is covering all small local level spaces. So Hilbert space is nothing. So main thing is to understand the vector space. Okay, the Hilbert space. If we are talking about the Hilbert space, this Hilbert space definition is coming from the physics and mathematics both. So the Hilbert space is nothing. The spaces like kitchen space, spaces like drawing room space, like that, all that is local level spaces. If we are covering here, suppose a bedroom space or something, all that local level spaces we can keep in a home. So this we can call it as a home. Our home is there. Okay. So this home is covering all that local type of rooms and spaces, right? So the kitchen space, all that spaces. So this is analogy of the Hilbert space. So this is the bigger space we are saying, which covers all the local level spaces. So the Hilbert space is the ultimate space which covers everything. Everything means local space. We are talking about X, Y, Z axis. That means these are the direction level coordinations right here. So all these levels are covered. So these spaces also is the Hilbert space. Vector spaces we are talking about. Vector space, the components of the vector space is also in the Hilbert space. So whatever the space, small level, local space level spaces we are talking about. So spaces are nothing, only the some definitions of terrorities, right? So whatever the things or terrorities we are talking about in the local level, everything is covered under the Hilbert space. So Hilbert space is the broad level space, right? So that's nothing special in it. So okay, we are moving towards the now matrix elements. So you are free to chat with me. Okay, you can put your questions, you can put your thoughts, what you required more. So maybe I will cover that things in my forthcoming speeches. Yeah. So if there is any doubt or something, you can also type on the chat also. So time to time I will see the things, and maybe in the last we will have some that queries responding section. So yeah, now coming to the matrix as a operator. So here in the mathematics, so when this concept of mathematics has been developed, and we have discussed that this Deuce has formerly the Turing machine has given the concept of Turing machine, quantum Turing machine in the 1985. So, when they have given this concept as a Turing machine, so they also has given that in that concept we have to compute. So for that computation, we requires some operators. So that operators, they have suggested, use has suggested that that operator should be a matrix operators. So we require the matrix there. The role of the matrix is nothing. Everybody knows the role of the matrix is a basic, very basic level, 11th level computation thing. The role of the matrix is to arrange a lot of things, lot of dimensions, a lot of elements in the systematical order, so that we can choose in a systematical order, we can compute, and we can communicate the systematical order to the any other order, like rows, column rows, hybrid. So all these are the systematical things defined by the matrix operator. Okay, so we have to use the matrix as the operator here, and their linear combinations. Yeah, and their linear combinations. So the linear combination means everybody is just involving in it. Linear combination, what is the meaning of the linear algebra? So meaning of the linear algebra is nothing. It is called superposition. So the word linear combination itself giving the superposition. And we require this superposition in the quantum. That's why we are using this linear combination, right? So all these things now only inner and outer products are remaining. So all these things are formed the basic foundation in the mathematics. We required the knowledge of these things. We require the tools, how to use the matrix, how to use the vector space. Vector space mean to say there are two things only. The vector space mean to say whenever we are talking about the vector space, that means there are two things: inner product and outer products. Right? Inner product, everybody knows, but if you will talk about inner, nobody knows. If you will talk about dot product, everybody will know. Yeah, this is a dot product. Outer product, it's a tensor product. So sometimes the candidates may be knowing this tensor, or sometimes they may not be knowing this tensor. Okay. Sometimes in the BTech mathematics, in some of the syllabus or curriculum, they are having the tensor. In some curriculum, they are not having the tensor. So you can go according to that. If they are not having the tensor, you can clear the tensor. The tensor, I can show in a one line. The tensor is just nothing. It's only the expansions of whatever the dimensions we are having. So whenever we needed different dimensions, we needed to expand in the dimensions. Suppose we are having a x, y, z dimensions, x, y, z dimensions, right? Now we need to expand these dimensions. Okay, so there are some more uh, beyond the three. Only these can give us the computation power of where the dimensions is only three. But what happens when there are dimensions of five? Then we need to expand these dimensions. So when we are needing to expand these dimensions, the dimensions can be expanded by a tensor product, right? Exactly, this is the definition what I told you. This is the definition where the tensor definition has arose. Initially, this is what the concept by bringing the tensor. Okay, so yeah, so the tensor product is used to amplify the dimensions or expansion in the dimensions. Okay, one example I can give you in the also in the kitchen and drying space area. So 1 minute. Suppose in a drying room area. This is the drying room area, and this is the kitchen space. This is the kitchen space. This is the drying room space, right? So in the kitchen space, suppose we are having a vectors. What vectors? Suppose we are having a milk. What vector? Suppose we are having a rice. Is a raw material. That's it's a vector. We are having a atta. It's a raw material. It's a vector. Suppose, right? Suppose for the drying vector, we are having the elements TV. We are having the elements sofa. We are having the elements whatever you can call it, chairs, right? But we need to define collectively the dimensions of the both. Collectively dimensions, so the collective dimensions, we are talking as a home. So when we are talking collectively, we can talk as a home, right? So in the home, now when we are going to define the vector components of the home, so we cannot define like that. TV is the one component, sofa is another component like that. This is not. We have to go for the linear combination. So that means we have to go to the multiplication and permutation and combination of all these three to these threes. So the permutation combination like this: TV and this, then TV rice, then TV atta, like that. So then sofa, this one, this is mapping and nothing else. So this is mapping. So this chair with the milk, chair with the rice, chair rice, then we can call it chair atta. So all these there, 3 plus 3 plus 3 like that. So the total there are 9 components now. So that how we are expanding the dimensions of the home, of our home. Now our home is expanding the 9 dimensions. So that the decoration or the things of the whole home. That means we are, if we are talking about the kitchen space also, or we are talking about the dining room space. So both are related to the home now. Now for the home, there are 9 certain parameters or dimensions. We need to take care of that. So that means what we are doing the kitchen space is having a 3, this having a 3, but now we are having a 9. So we are diversifying our dimensions. Okay. So only that this is called a tensor product. This is called a tensor. So how we are multiplying this permutation combination, this is called the tensor and expansions of the our vector quantities. All that. So this is nothing. This is only the tensor things. Okay. You may be thinking that how we are uh, engaging these things in our quantum. So let just wait. We will collectively see how these are important in the quantum space. So now we are introducing a now. Now I think all of you are ready for the qubit. You know everybody's that qubits. You are teaching qubits already. So this qubit is nothing. We can call it as a quantum coding. We can call it as a quantum coding. And to represent these qubits, we need a certain different level of mathematics, right? And that different level of mathematics, because what we are doing, we are picking the concept from the physics. And when we are going to pick up the concept from the physics, so the concept for physics means quantum mechanics. So we have to see the quantum mechanics is dealing in what quantities. So when these things are observed, then it was observed that the quantum mechanics was dealing with uh, the quantum mechanics are dealing with first matrix matrices, then they are dealing with the linear algebra, linear algebra. Then they are dealing with uh, the last most important thing is they are dealing with the cat and bra, the cat bracket and bra bracket like that. So these are the brackets which is we are used in the quantum mechanics. Okay. So the spin Pauli matrices. So all these are the pillars of the quantum. So we were dealing in these matrices, linear algebra in the cat brackets and bra brackets like that. Okay. So what is the concept of that? Oh, only I can initialize this concept like this, that we are having the bracket like this. Okay. So this is the bracket we are using already using in the codings, right? So iOS team and all that. So when these type of brackets are there, so what we are doing, uh, not we physicists, they have divided this bracket, and this portion they have called as a bra bracket, and this is portion they have called as a cat bracket. So these were the notations of the quantum mechanics. So we need not to be go in the detail because we are not the physicist here. We are only the part of this quantum computing. We are studying as a physics only. So that we have to pick up this notation. Okay, because everything is dealing in these notations. So we have to pick up these notations from that quantum mechanics, polymatrices, and all that. So whatever Schrodinger has developed this quantum, then later on some more scientists are there. They have developed. So we have to directly pick up that notations. That notations is called bra vector and cat vector. So ultimately, so this is a bracket. So this portion we can call it this one, and this portion we can call it this one, and nothing else. Okay. If we will clear these things to the students, so I don't think so. So I have not experienced like that. So they will understand very well like this. So this is called bra vector and cat vectors, right? So that on coming to the properties of the bra vector and cat vectors, so these bra vectors are horizontal. That means these are the rows matrix, and this cat vector are the column matrix like this. There is a difference, and even though these things are coming directly from the physics or directly from the physics mathematics, what we are doing in the polymatrices, so this bra vector are dealing with the horizontal matrix, and that this cat vector are dealing with the vertical matrix. That is, vertical matrix means to say column matrix. Okay. So there is a one relation why these are so like this. So there is a one thing that there is a concept in the matrix. The concept in the matrix is that if you will take a transpose of any matrix, so what we are doing, we are doing row to column exchange, row to column exchange. So when we are doing, so this is the same thing as that. So that means the cat and bra vectors both are transposed to each other. If you are taking a transpose to the bra vector, you will get a cat vector. If you are getting a reverse, that is transpose of cat vector, you will get a bra vector. Okay, so these are the things how to represent the codings, these quantum codings in terms of bra and cat vectors. Okay, so the cat vectors are the column vectors, bra vectors are the row vectors. Okay, so okay, let me clear all these drawings. Yeah, so now the probability amplitudes. This need to be defined more. So probability amplitudes, yeah, yesterday we were talking about something discreteness and continuous natures. So directly I have quoted and I have picked up the concept from the de Broglie. And I have given you that de Broglie has said that a particle nature and a wave nature. Okay. So that means if the particle is moving this one, so we can understand this as a particle is moving like this. So we can understand as a wave moving. Wave is moving like this. Okay. So when we can understand the wave is moving like this, so what's wave of what? We have to take the questions for this. Wave of what? In the wave, when the waves we are seeing in the water, we are seeing the waves of the water. When we are seeing the waves in the string, we can say the waves are of string. But at here, we will say the waves of particles, waves of the particle. And when we will say this waves of the particle, as de Broglie is saying, the waves of the particles. That means the any point or any particular location in the wave, localized location like this, or like this, whatever. Any point in the wave, we will represent this point as the marker for the location of the particle, as a marker for the location of the particle. So that means, as described earlier, so we are not going out abruptly from 0 to 1 or 1 to 0 changes. So here location of the particle or presence of the particle is changing slow by slow, percentage by percentage. So 0, 5, 10, 100 like that. Okay. So gradually it's going changing. Okay, not abruptly. So this is the continuous nature. So when there is a continuous nature, so we will see the probabilities. So we will deal with the probabilities. Okay. So these probabilities, so I also quote some examples for these probabilities, so that the unconventional things, the quantum has compelled us to think about that. If particle is present at some point A, so we have to say we have to say unconventionally, yeah, so the particle is present 90% there. Our mind will not accept, but yeah, this is true. So we have to say so. To represent these things, that we are representing a 90% or 10% like that, I want to just quote some of the examples of daily life. So how we are dealing with the probabilities. So that we will quote and we will give some examples. As I personally believe that, and everybody of you will believe that like this, that examples will make the clear path of the this new entries in the quantum. So, so example, I'm quoting like that. Suppose a one person is ordering a suppose a one person A is ordering a food for the another person B who is a friend of him. Another person B who is having a friend of him, right? There are the distance location. Suppose he is ordering a food, and when he is giving the order of the food, so maybe suppose this person is liking the most paneer, okay, cheese. So suppose and this person is ordering a pizza, okay. So and this B person knows that he may order a pizza, and but he knows that he likes most of paneer, so maybe possible he can order a paneer also. So I will give you the example of the superposition thoughts coming in the mind, right? So that everyone can understood easily. The B person will think like this. They will have the thoughts having a different possibilities and probabilities, right? So the thoughts may be like this. So there are two things. First is pizza, then another is paneer. So they will give their mind to this level of thoughts that may be possible the 90% pizza will come, and it is possible that 10% paneer. Only the 10% possibility is there that paneer will come. So in another thought, this is one thought, T1. This is one thought. In any other thought, T2, maybe you will think about that. No, 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 no. Maybe possible. These are 50-50% chance. So there is a 50-50% chances of ordering a pizza and ordering a paneer. But even though you are not knowing this, all these things are in a wavy things. Okay. So one wave is like this, another wave is coming in your mind like this. So wave is like thoughts, right? The thoughts having a different possibilities. So suppose in another possibility, another possibility, you can think about like that. Oh no 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 no! He knows very well. He knows me very well. So maybe he will order 90% paneer because he knows me very well. So that means 90% of paneer, or maybe 10% he can order a pizza because of forgetting nature. So you can think like this. So these are the permutation combinations when you will talk about. So that I was talking yesterday, this permutation and combination pairing of this 90-10, 50-50, this 90-10, then the 70-30 you can also have. So theoretically, there is no limit of stages you can thought about. So these are the only thoughts, and these thoughts we have to catch up. If anyhow we are catching these thoughts and converting these thoughts in the reality, every thoughts, converting all these thoughts in the reality, we may be able to play with the states or input states. What we are talking about is study. We want to increase is input states. So, so these are the thoughts and analogous to the quantum states in the superposition. Superposition means to say that in this thought, suppose in this thought, there is a superposition of paneer, 30%, of superposition of pizza, 70%. So all these thoughts are superposition thoughts. So all these states are called superposition states, like that. But the problem begin here when this pizza boy or delivery boy will come to be. So he will deliver only one possibility among all that infinite possibilities. Among all that infinite possibilities, he will deliver a one possibility. He cannot deliver all of the possibilities, 90%, 10% like that. He can deliver one possibility, or there are 100% chance that either he will deliver paneer or he will deliver a pizza, like that. So this is the restriction in the quantum. So when the order has delivered to the B person, that means B is measuring their thoughts. Now, when that thought is converted into reality, we have come across here that in reality, there is only and only among these two states we can have. Either we can have a pizza or we can have a paneer. This is the reality. So that means this is the restriction. When we are measuring the superposition states, when we are measuring the superposition states, we have to be in a either of the one state. So that means we can play the superposition states until and unless it will remain superposition. As soon as we are going to measure it, it will again convert it into the reality. So that thoughts will convert into the reality, and another language we can say that all these states are collapsed now. As soon as the delivery boy has delivered these orders, all that states has collapsed and converted into the one state, either this state or this state, right? So this was the small level efforts to clear out what are the superposition states and how they are collapsing when we are going to measure it. So the same case happens with the quantum computation also. So yeah, superposition states, we are able to define the superposition states, and we are able to discriminate the superposition states. We will talk about more in the hardware section that how we are controlling and catching these superposition states. So there is no method now there is no method that we are catching the thoughts. But yeah, in the hardware we can catch these thoughts. Okay. So in the hardware we can have the superposition and mixed states, but but in all over the superposition and mixed state, when ultimately we are going to measure, all the states will collapse and convert it into the one state. Okay. So that is the game of all these things. So So as soon as this quantum coding is concerned, now with moving ahead with that example, the qubits, they are the 2D vectors. We are dealing with the 0 and 1. So here in this real interface, we have to deal with the 0 and 1, not with the pizza and paneer. We have to deal with the 0 and 1, and along with that, we have to deal with the superposition states of 0 and 1. The superposition state of 0 and 1, right? So, as we have talked about the this Bryant cat vectors, okay. So naturally, uh, the these states 0 and 1 state, we are representing them as a column. Yeah. So we are representing as a column matrix all that 0 and 1 state. We are representing as a column matrix. So that column is like this. These are called the basic vectors. So these form the basics of the this qubit. So this is called cat 0. This is called cat 1. I'm not efficiently going in these details because I know that everybody is teaching this, and when everybody is teaching there, they will know how to move ahead now. Okay. So these are the starting acceleration I want to give all of you, that yeah, that use these tools. Uh, 1 minute. Yeah. So this cat 0 having a matrix form. The matrix form is that 1 0. The cat 1 is having a matrix form. Sorry, there is a mistake, 0 and 1. Like this. So the cat form is a matrix form that is called a 0 and 1. And these are the column matrices. And if we will take the transpose of this matrix, when we will take the transpose of these matrices, then we will have a column, this row matrices like this. So these matrices are cat. Cat means we have to represent like this, like this. So yeah. Now, geometrical interpretation using block sphere. So this block sphere, all of you are teaching the block sphere. So block sphere is nothing new. Uh, So only this is only there is not a single rule of this. Only they are not having a physical representation, but they are only to representing the qubits, amplitudes and phases. The block sphere only to represent the phases and amplitudes. So how to represent that ones? So to represent that one, again, I want to take the example. 1 minute, let me see. Hmm, like this. So we were talking about the block sphere. The block sphere is nothing else, only representation of basic states 0 and 1. So first of all, I want to take example of I, j, k, and x's. So this is the x, this is the y, and suppose this is the z-axis. Okay. So in the x, usually from the 11th classes, we used to take it unit vector I, unit vector j, unit vector k, along the x-axis, y-axis, z directions, right? So these are called the unit vectors. Why they are called the unit vectors? If we want to represent some location of the point, so we have to take the help of this I and j. So we have to multiply I at how much units we have to travel, 5, 6, or 7, whatever. Suppose there is 5a plus 7j. So what we are doing, we are traversing 5 units in the direction of I, and suppose 7 is there, so 7 units in the direction of j, or y direction. So I, j, k are also representing the directions and also representing a unit quantity. So that means 5 multiplied by unit quantity, we have traveled in the I direction, x direction. 7 multiplied by the unit quantity, that is 7, we are traveling in the y, z direction, y directions, like that. So x, y, z or I, j, k, the x, y, z are the basics and I, j, k are the unit vectors along the directions. So like that, we are representing all these things 5i plus 4j plus 7k, like that. Like that, we are representing ijk. We have to take the basic vector. The basic vectors at here are only 0 and 1. If we are talking previously, we are talking about 0 and 1, but now we have introduced the this cat vector. So that means we will talk about cat 0 and cat 1. So these are the basic fundamental ones, the cat 0 and cat 1. These are the two states. On measuring the superposition state, we will return to these either 0 or 1 state, right? So that means whatever we are doing, whatever we are going on our dreams, okay, just go in our dreams, but whenever we want to return in the reality, we are returning in the either 0 state or 1 state. So superposition state is the state of the intermediary things, you can say, that we are starting with the 0 and 1, and ultimately we are, when on measuring, we are left with the 0 and 1. Okay, we are starting with the 0 and 1, we will start from that and ending with the 0 and 1 on measuring, right? So the superposition states are the only and only, you can say, the intermediary steps which is used to calculate the speedy things in the quantum. Hmm. So, so here in the quantum computation, when we are talking about the cat and bra vectors, that this zero, cat zero and cat one will form the uh, basis of the quantum computation, just like in IJK. So we have to represent whatever the superposition states are there. So these superposition states, we are saying theoretically they are infinite superposition states of having a different possibilities of 0 and 1. So so when we are saying that, that means we have to take this as a basic state. So as we are writing in the case of J, IJK, we are writing like this, 7I plus 5J like this. So that means these are the basics. We have to take it. And here also we have to take, because these are the basic states 0 and 1. So we have to take whatever the possibility is there, 70% possibility of there of 0 state, 30% possibility of in one state like this. So we have to take this 0 and 1 as the basic vectors at here. So whatever the permutation and combination you will be given, that suppose 20% chances of being in 0 state, then there is a 80% chances of being in one state like that. There may be a 31% chances of being in 0 state plus 69% chances of being in one state like that. So all these states are called superposition states. And these superposition states, this in this way we can represent in the basis of 0 and 1 like that. So if we want to give to the general notation, so the general notation we want to give that this is the general notation for this. Yeah. So this psi notation again we have brought from this quantum physics, that they are Schrodinger is used like this symbol psi wave function. We used to call it the wave function. That's why here we are taking the same notation. The wave function we are representing in a general notation as we were saying the 70 or 30%. So here there is a alpha. So alpha possibility. So we will read this like this. There is a alpha possibility of being in 0 state, and there is a beta possibility of being in 1 state like that. So as we were talking about, we are taking 70 and then we have to take the 30. That means why we are taking this 30? The both should be given a 1. And the reason of why we are taking a mod, so reason of this is lies here in the wavy nature. So, so these wavy nature, we are talking about the waves of what? Wave of the particle. And we are also talking about that. That means the localized point on this wave will represent the location of the particle, or will represent, give the possibility of the finding the particle. So, but here, when the positive node is coming, then it is okay. But when the what happens when the negative node will come? So when the negative node will come, so the possibility of finding the particle is going negative. Now this is against the law. How can the possibility can go negative, right? So the possibility cannot go negative. So one of the possible solution for that, which is also governed by the bonds, this is in the quantum mechanics, that the possible solution we have to square to everything. If we will square like that, it will go like this. Square, it will go and come with upward like this, square like this, square like that. So that's why we will square everything, have alpha square plus beta square like that. So this alpha square plus beta square should come out to be unity. And this condition is called the normalizing condition. This normalizing concept is again from the physics, right? So whatever I needed to rooted this quantum subject from the physics that I explained yesterday. Now here need not to be go in detail with the physics also, okay? Because that same concept will work here. If you are getting that concept to the students, the same concept from that same concept you will driven here to the students. Okay, so like that. So hmm, now now ultimately we are coming to the blogosphere. So in the blogosphere only is it is a representation thing. So when it is type of representation thing, So when we are taking ICK, so we are taking the basis for that. This is the Cartesian coordinates and the Cartesian axis x, y, and z. We have taken this frame. So instead of that, now we are taking a frame of sphere because we have to deal with a lot of superposition state also. Okay. So when we will deal with the sphere, so in the sphere, suppose this is the north and south of the sphere. So in this sphere, we can suppose this cat 0 at one position and cat 1 at another position like this. And all over the surface here, 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 all over the surface, as we will rotate on the surface of these things, we will see that there is a combination of 0 and 1. All these states are called superposition states. So this superposition state combined the 0 and 1 in the different angles, right? And what is the concept of that different angle and phases? The concept is lies in the wave also. So what is that? So this is also inherent in this interference principle. So whenever the two waves are coming, so it may be possible they are the hump is falls on the hump like this, and somewhere it is also possible that opposite like this. So when this will be the case, it will cost you a minimum intensity or minimum amplitude because this amplitude and this amplitude will get cancelled, and this will give you a maximum amplitude. This will give you a maximum amplitude. This will give you a minimum amplitude. It doesn't means that we will deal with the maximum minimas. No, we will not only deal with the maximum minima. So in the process from this to this, in the process from this to this, there will be when these two waves are interfering each other, there will be conditions having the mixed state between the maxima and minima. When there are mixed state between the maxima and minima, then these mixed states, we want to represent that mixed state as a superposition states. Okay. So, yeah. So, this maxima and this minima, these are the results of interference. So, when we want to, suppose we have coded all the inputs, suppose we have coded some of the inputs, information input data to our quantum circuits or quantum computing circuits. So, that when we are encoding in the quantum circuit, that will be in the superposition state. And when they will be in the superposition state, so that means everything is representing as a wave. So all that waves combining and will give you the resultant superposition waves here. This is the resultant wave. So now when we are going to measure, we have to decode this interference. How to decode this interference? That decoding can be done in the two ways. Either we can do such type of manipulation that it will result in the maximum amplitude, or we can do a such type of manipulation it is resulted in the minimum amplitude. Okay. Now when you will say these things, the student will get confused. So what is this manipulation? So that manipulations we will study in the algorithm part. Okay. So but yeah, so when you will do such type of manipulations, so that manipulation is coming giving the maximum amplitude, that will be given like this. And maybe sorry, uh, and maybe some of the manipulation may give you like this results. So we are free to choose either of the manipulation. That choosing of the manipulation is the designing of the circuit. The what manipulation we are choosing, that means according to that we will design our quantum circuits. Okay. So this is the play of the story of this superpositions and interference like that. Yeah. So I have thought that I will discuss this in the hardware section, but some of the information I have to discuss it here. Suppose in the qubit, what are the physical things? Physical things is that we want to represent uh, 0 and 1, and apart from 0 and 1, we want to represent the superposition state also. So for the 0 and 1, for the atomic qubit transition, we can represent any parameter. You are free to choose the parameter. Any parameter we can represent to 0, any parameter we can represent to 1. So suppose at here, so we are, what example I am showing here, in this example, we are taking the ground state and the excited states of the atoms as the parameter. So when we are taking the ground state and the excited state as the parameters, so that means we are free to choose we are free to choose here ground state as a 0. We are free to change excited state at a 1. Or you can also go on the revert process. Revert process means excited state you can choose as a 0. No problem. And ground state you can choose as a 1. Okay. No problem. According to that, you have to reverse the circuits. So any of the states, any of the sensing things, we can choose in as a 0 and we can choose in as a 1. Okay. So all these notations I have talked about. So yeah, 0 and 1, all this I have talked about. Blogosphere. So entanglement yet to be talked about. So yeah, this is the ultimate beauty or ultimate demand of the nature. What is this slide is all about? The unitary operators. The unitary operator, we are dealing with this unity operators in the quantum. And if somebody just like before, we have discussed about the discreteness and continuity. So this quantum nature is a demand. The quantum thing is the demand of the universe, or demand of the nature. It is not the demand of us that we have lag behind of the classical computers. So like that, when we are moving towards the quantum, so there is a demand from the universe also, that universe wants everything is to be reversible. Okay. So in the universe, in the nature, everything is a reversible. Everything. When you will go in the broad sense, the years have passed, the years have passed. So you can say the nitrogen cycle, you can see the water cycle, you can see the mineral cycle, you can see the fossil fuels that has escaped from the ground, minerals from the ground, mining, all that are used in the product, and after the using the product, that product is again going into the dump, and the dump converted into the earth reservoir. But after so many years, that process is so much long. The fossil fuels is a so many long process, but process may be long, but this process is the ultimate truth of the universe. So every process should be like that. It will be a reversible thing. Every process should be like that. It should have the reversible things. So this is the demand of the nature. So Deuce has understood this demand. Firstly, Feynman has introduced the concept, but Deuce has understood this demand. And when Deuce has understood this demand, they have said that, yeah, that in the quantum, we will do these things, that we will deal with the reversibility things, which is absent in the logical gates, apart from if we'll exclude the NOT gate. NOT gate is the reversible, but AND gate or OR gates are the non-reversible gates, right? So the reversibility is the demand of the nature. So when we are running this concept of building a quantum Turing machine, the Deuce has said this, when we are building a quantum Turing machine on the nature principle, then why not we will keep this demand as it is. So we have to keep this demand as it is, and this reversible nature is defined by unitary operator. So this is the physical world, the reversibility. Reversibility is the world, physical world. But Every physical world needs a language of mathematics. So when we will go into the mathematics language, so in the mathematics language, that reversibility world is the transform of unitary. So what the operation we want to perform, we can perform the unitary operation. We want to perform the unitary operation for the reversibility. So in the mathematics, if we want to perform the operation of the matrix, so matrix operation has to be unitary. Okay. So the unitary operation is the first demand of this quantum gates. Okay. So the matrix representation of the gates, that's all that Deuce has suggested. We want to represent the matrix as a gate. We want to represent the quantum gates as the reversible rotations. And the reversibility itself saying that reversibility itself saying that we we are having a non-degenerate outputs. Non-degenerate output means to say there is no fan in and no fan out. So what do you mean by fan in and fan out? So suppose in a classical gates, we are having this. Suppose AND gate. So when this we are having a many, there's a two inputs, input one, input two, and there is one output, right? So when we are going into many into one, this is many mapping to one, many to one. Okay. So when we are going like that, so this is called the fan out. Okay. So many into one or one into many, one into many. Okay. So these concepts are the irreversible concepts. Irreversible concept means when you are going in fan out or fan in way, so you cannot make the reversibility possible because when you have mixed this and this state to this state, you cannot go reversible. So like that, you are having a water. Suppose, for example, you are having a water at the 30-degree temperature, and you are having a water at 0-degree temperature. So you are mixing these waters. It will make you, suppose it's giving a 15-degree temperature or resultant water. Now you cannot, this is the irreversible condition. You cannot return to the same zero level of 30 level condition. Okay. So this irreversibility is not allowed in the quantum because quantum is making nature friendly things. So what the nature is saying to us, quantum as it is implementing. So Deuce has said this, yes, this fan in and fan out is not allowed. That means non-degenerate outputs. Okay. So that means to one. That means in the quantum gate, what we want to retain at here, we want to retain one to one mapping. If there is a one input, there should be a one output only. One output only. For the one input, there will be one output. And if there is a two inputs, there should be a two outputs like this. If there are three inputs, there should be a three outputs like this. Okay. So one to one, cut to cut. That is the demand of this uh, quantum computers. And one of the advantages in the hardware side, because I have developed many quantum optical gates in the hardware side. So what I have realized of this reversibility and irreversibilities in the semiconductor chip, when we are forming the semiconductor chip. So in the semiconductor chips, when we are forming a buses inside the CPUs and architect, so that buses we have to perform the machine assembly languages, interface languages, we have to perform some logical operations. So what we have realized, this is my personal experience, what I have realized that in performing these operations, when there is a talk about go to the reversible path, suppose I have fixed this bus for this path, bus one. So when we have fixed the bus one path for this AND gate, and when we are instructed to return into the initial state, what we are doing for the returning, we are doing in the returning only a hardware engineer can understand. So I am basically hardware part of things. So I can know better. That same thing I'm telling here. So when we are instructed to go back, we are designing a new circuit, a new bus. We are allocated a new bus for returning in the initial stage. And this new bus is the unnecessary expenditure to us. We are having a very much low size in the nanometer size, and somebody is saying in the nanometer size, just perform this input highway and returning highway also. So unnecessary, we are overburdened for this. Okay. So that, but it is coming by default in the classical computers, that this is the irreversible condition. So we have to design in another bus for this condition, returning condition. But what I have faced, yes, in the quantum computation, I have faced this is only I have to design a one bus for this. Only I have to design a one bus, because this gate, whatever the gate we are using here, every gate is, we are developing knowingly. The classical computers has developed, but does have developed at enormously. So like that, somebody has developed, we have adopted, somebody has developed, we have adopted. Now here we are adopting the principles of quantum in a chosen way. We are very choosy when we are developing the quantum. So it's just like a planned city. So in India, I have listened about Chandigarh. So Chandigarh is a very planned city. So in the planning city, suppose in a Bangalore or some other cities, they are developing attractively like this. So in the planned city, what is the advantage? We are already planned the drainage system. We are already planned the flooded type of situations. Whatever the things are, we are planning. So like that, we are developing. The quantum computation is the developing stages, right? So very small parts have been developed. So when we are planning this pathway of the quantum computing, so yeah, knowingly we are choosing this, and this is giving a very much good advantage, that we need no extra circuits for returning the instructions. So if we are said to rooted a return state, then there is no problem for hardware side. So we can return in the same bus like this. The input is converted to the output, and when it is said to return, output will return to the input in the same bus. There's no need of extra circuit or extra buses to be installed there in the architect of the quantum computation. So that is a real advantage I have faced here. So yeah, okay. So that is the unitary operator. So now from this conversation, it has been clear that there is a demand of the nature that we have to go for the unitary operators. So all these things are said by the Davis. So first he is conceptualized the requirement for the quantum tuning machine. So gate must be unitary. So whatever the gate we will develop that gates will be a unitary. Unitary means reversible. And another thing is that we have to take in the mathematics formulation. So for the mathematics formulation, we have to take the matrix-based transformation on the qubit. So all these things I have discussed. So single qubit gates. Now we are starting with the single qubit gates. So already the Deuce has introduced these things, that we need a reversibility condition. We need this is one like that. When he is designing a hypothetical quantum Turing machine. Turing machine, everybody knows, I think. Turing machine is the hypothetical one. So Deuce has also designed the hypothetical one for the quantum Turing machine. And he has said that what are the requirements for that Turing. So the reversibility was one of the requirements in that Turing. The matrix are the another requirement. But in 1995, there is a one paper. I have that paper, the elementary gates for the quantum computation. So that paper is written by this Berenko and all that colleagues. They have said that they have used this poly spin gates, poly XYZ. This poly, don't get confused. This poly again comes from the physics concept when we are developing the quantum mechanics. In the spin of the electron, we are developing the theory for the spin of the electrons. So the electrons having a 1 by 2 spin, plus 1 by 2 or minus 1 by 2 spins, that is not come as it is. That comes from the Pauli's derivation. So the Pauli's matrices has been developed so much 50 or 70 years earlier in the 1925. So 1995, when elementary gates, they were designing, the Berenko designing elementary gates for the quantum computation. So they have used these poly gates, XYZ gates, as the elementary single qubit gates. So that has represented that these operators combined with the control operations that is giving the universal gate set. Okay. So now in this way, this Berenko has introduced this poly gates and the matrices for that gates we have directly picked up from Pauli's matrices. The Pauli has developed these matrices in while formulating the quantum mechanics. The spin 1 by 2 1 minus 1 by 2. They have developed this matrix. That matrix we have directly picked up from that. So that matrix I'm showing it here. So matrix are like that. So it is having a 2 cross 2 matrix. So this matrix is a complex one. So it is introducing the complex symmetry. But this matrix and this matrix, these matrix, there is a difference between these matrix. This matrix, the basic nature of this matrix in the Pauli, what Pauli was doing, Pauli was evolving the theory for the electron. The electron is revolving clockwise or revolving anti-clockwise. So in the clockwise revolution and in the anti-clockwise revolution, they need some operation, matrix operation to be performed at here. So that's why they have given this. So in the polymatrices theory, this X is just changing the clockwise to anti-clockwise. That means it's flipping the rotation of the electron. That was the work of the poly. So it is changing the rotation, that is clockwise to anti-clockwise. It's changing. So that means changing the clock to anti-clockwise. That means they have changed, flipping the condition of the electron. So and that is the condition of it here, X gate. So, so by having the same aim, that if we will give a zero, it will change to one. At here, because at here there is a two things. There is a clockwise spin, or there will be an anti-clockwise spin, right? So here there are two things, zero and one. So clock, when we are applying X, it will change to anti-clockwise. Anti-clock, we are applying X, it will change to clockwise, like this. So at here, same work we will perform at here. When it will apply to zero, it should give one. When we'll apply to one, it should give zero, like this. So, so these are the works for the polymatrices. Yeah, the matrix of the Z is to shift the direction only. Is to shift the direction. That is 1 to minus 1. Okay. So uh, these are called the unitary operations. Ux, Uy, or we can say Uz right here. So these are the matrices. How to develop the truth table for this? Yeah. So in the XY gates, so what they are doing? They are just see the things. Things are like this. 1 minute. Um, hmm. So we are having three things in every inputs. One thing is that we are having a pure zero state, pure cat zero. There is a 100% possibility of pure cat zero. Or we may have a pure one state. There is a 100% possibility of pure one state. Or we can have a mixed state, that is we are calling a superposition states, and we have picked the symbol for that from the quantum mechanics, that is psi. Psi is the superposition states, and in a generalized form we are representing like this. There is a alpha possibility being in zero state plus beta possibility being in one state. Okay, these are the three things. And there is another story that we can resolve the superposition states into infinite states. That is another matter. But on a general statement, On a general statement, we can say that these are the three inputs we can have. So for these three inputs, when we are applying a X gate, so the X gate is just what they are doing. They are flipping the conditions. Suppose we are talking about superposition because every student is taking this superposition is a very tedious job. So suppose we are applying this superposition condition. So this superposition condition, in fact, this condition we can represent as a superposition. What? Because one component is 100%, another component should be 0%. Here one component, 1 is in 100%. Another component should be a 0%. What is that component? Here there is a 1, so this component of cat 0. Here there is a 0, this component should be cat 1, like this. So we can represent superposition state like this. So this is also a superposition state of 100 0 permutation combination and 0 and 100 permutation combination. So what they are doing when we are applying a X gate on it, suppose this is a condition. We are applying a X gate, okay, and there is a linear algebra. Linear algebra means we have to multiply as we are doing the matrix multiplication. So this is the matrix for the X state, X matrix, poly X matrix. This is a matrix for the zero state. Zero state means 1 0. So it is having this state. So see this factor 1. So it is having a 1 probability. Probability maximum can be 1, that is having a 0, like this. So 0 state having a possibility of 100%, that is 1, plus there is a 0% possibility, that is 0 probability of in one state. So this is represented by this one. So when we are applying towards the transformation matrix, when the transformation matrix we are applying, so we are getting this result.
So your friend. Sir, I'm sorry for the interruption. Actually, your voice is too low. We are not able to hear.
Ah, okay, okay. Mm, now, now the voice is clear.
Yes, now better, sir.
Okay, 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 okay. Yes. So here, hmm, so here we are representing this psi as a one state. Okay, this state is the representation of this psi, and representing by 1 0 column matrix. Okay, and this is the transformation matrix, unitary operator. So when we are combining this in a linearly means only simple multiplication we have to do the matrix multiplication. That's why we termed this as a linear. So when we are multiplying, so you can perform the multiplication at here row by column like this. So we will get this one. So another this is for the Y gate, this is for the Y gate, this is for the X gate. Okay. So same things we can apply in the Y gates. So what we are seeing when we apply the Y gate, it imparts the I factor, this I factor in this Y gate. Okay. So it imparts the I factor, it here, it only nothing like this. So this is for second input for the Y. So like that, we are computing X and Y gates. Hmm. So for the Z gate, Z gate matrix is also there. We are having Z gate matrix at here. So in the Z gate matrix, this is the matrix. So ultimately, it will impart a negative term in the final output. So let's see Z gate. It will impart the negative term in the final output like that. So there is a negative term and nothing else. Okay. So what we have to do, we have to perform the matrix multiplication, that is a linear algebra. Okay. We have to perform the matrix multiplication and we will get the results in the X, Y, and Z leads. So ultimately, when we'll combine all these things, we can see there. So these are the things. See the notifications things. So X, these are the inputs we have to apply to every gate, right? So when the 0 is applying to the X gate, we are getting a 1. When 0 is applied to the Y gate, we are getting this I factor. When 0 is applying to the Z gate, Nothing will happen. But when 1 is applied to the X gate, we are seeing that in inputting 0 to 1 or 1 to 0, the X gate is just reversing. So that means this X gate is working like a NOT gate. In the Y gate, what we are getting? We are getting a phase factor I and phase minus I at here. When we are applying 1, 1 is converting into the minus I, 0 is converting into the adding a phase of I here. In the Z, 1 is converting to the minus 1. And the same thing is applying here. Okay. So these are the results of the single qubit gates. So these single qubit gates are performing the unitary transformation. Unitary means reversibility. Unity means reversibility. If we will form these inputs, then we will get this. If we will consider this as an input, we can get directly this ones. Directly this one. This is called reversibility. This to this to this to this, like this. This is called reversibility. This is unitary also. So when we are calling it, mostly students are confused in the unitary and reversibility. So both are the same things. When we are calling from the physics point of view, we can call it as a reversible. When we are calling in the matrix or operation, matrix operation, operator. So when we are calling in from the matrix mathematics point of view, we will call it as a unitary because we have to compute in the mathematics. That's why. So now coming to the Hadamard. Yeah. So in the Hadamard gate, the Hadamard has XYZ. XYZ is derived from the Pauli matrices. The concept was from the physics. So that was uh, that was derived much earlier than the conceptualization of uh, 70 years ago in 1925. So just like that, this Hadamard gate concept is also conceptualized in the mathematics. That was derived in the physics, the XYZ gates. The Hadamard gate was derived in the mathematics. So that this transformation is already existing in the mathematics long before the quantum computation. So the Deuce has also invented these things that quantum computing needs a gate that creates the equal superposition 0, 1. Because we needs to have a 0 and 1 superposition states. Who will create this superposition state? For that, another mathematic language has been used. That mathematics derivation was Hadamard. So Hadamard's derivation was such that it is creating a mixed state of inputs. So like this, it's creating that we are if we are applying 0, it's creating a mixed state of 0 and 1. When we are applying 1, it's creating a mixed state, but here there is a considerable difference. It's a marked, very much marked difference. This is punch line we can say in the Hadamard gate. So what is the punch line? So this is giving the constructive interference. So the interference was two types we have described. So one hump is occurring on the another hump. So we are getting a maximum output. Another is like that. One hump is occurring on the another hump. So this reverse in reverse condition. So we are getting a minimum output. So that minima is described by this one. So when we are giving the input 1 to the Hadamard gate, it is driving a destructive interference. And when we are giving a 0 to the Hadamard gate, it's driving a constructive interference. Okay. Actually, the sequence is like that, that these are the inputs. These inputs, suppose we will give to the Hadamard gate and we will create the superposition of these inputs. Superposition of these inputs, right? Then we will do the manipulations, we will do the calculations, all the operations at the superposition state. Superposition state is just like a wavy state. like this wavy state. We will do all iterations, all alterations in this wavy state. We will change the shape of this wave like this. We can change the frequency of this wave like that. Whatever the alteration we can do in the wave, alteration can be done in three ways. In the waves, alteration can be do in three ways. First, we can change the amplitude. Second, we can change the wavelength. Third, we can change the frequency. Or we can have the mixed of these things like that. Okay, like that. So whatever the alteration we want to give, whatever the changes we want to give, we can give this in superposition state. Ultimately, we want to retrieve the information from this superposition state. So when we want to retrieve this information, again this Hadamard gate will be used, because we know that this Hadamard gate is using an interference, this constructive and destructive. For destructive and constructive, both the interferences, we can use the Hadamard gate in the quantum circuits. Okay, so this is like that. So polygate cannot do this. We know, because polygates are first of all, polygates are one input gates, and the another thing is that polygates are not giving the output of superposition of both the inputs. Okay, their matrix are not like that. Their matrix are like that. They are used to alter the input state. Okay, so to create the superposition state, we have to use this gate, Hadamard gate. Okay, let's move ahead. So these are the single qubit gates. So the matrix for the Hadamard gate, this is developed much before than the quantum computation. Matrix was like this: 1 1 1 minus 1, and these are the rotation diagram. So this is the superposition state. So superposition is state of 0 and 1. Superposition of state of 0 and 1. So 0 and 1. There are two states. So it will have a 1 by 2, and it will have the magnitude 1 by 2. Probability of 1 by 2, probability of 1 by 2. Okay. Both have having the equal possibilities. So, and when we'll take the under root for that, because this alpha square is the squaring of this one. Okay. So when we will take the under root of that one, so we will get a 1 by root 2. Okay. So that means this superposition state, there is a 1 by 2, 1 by root 2 chances of being in 0 state, 1 by root 2 chances of being in 1 state. Okay. Why 1 by root 2? Because when we take the squaring of 1 by root 2, there is a 1 by 2. Then this is taking the squaring of this. Again, we will get 1 by 2. That will get a 1. This is called normalizing condition. So, so this is the input. This is the input, a superposition state. So this is a block sphere. So this is a 0. This is a 1. Okay. This is a superposition state. So when we are applying a Hadamard gate to this, when we are applying Hadamard gate to this, we are getting this result. This result means we are getting this is in minus state. Minus state means we are coming to this side. So this is coming to this side like this. Okay. So we are moving now. Till now, we have seen that there is a development of X, Y, Z, and this single qubit Hadamard gate. Hadamard gate among them is the most usable gate in the quantum circuit. So when we will use this Hadamard gate along with the combination of other gates, it will create the universality. Just as like in the classical gates. In the classical gates, we are having one model that is and NAND gate or NOR gates that were considered as universal gates. So at here, this Hadamard gate combined with this other gates will have the combination of universal gates. Will give the concept of universality. Yes. Now coming to the next mode, that is uh, CNOT gate. So this CNOT gate, in a very funny way, I have written this the boss mode gate. The boss mode gate means it is ordered by, or it is centered around the boss. So there will be a one boss. So first of all, there will be two qubits or two inputs, not a single qubit. Single qubit were like that XYZ and Hadamard gate, and there are two gates more also, SNT gates. And now there are two qubit gates. In the two qubit gates, we are having a CNOT gate. This CNOT gate is having a extra input of BOS. So extra input of BOS means like this. So this is a control. This is a target. Okay. Actually, we want to give the input to this, but to control this input, or to implement the condition, if and but conditions, we have implemented one boss here, that is control. So there are two inputs at the control and at the target. So when there are two inputs, so the symbol is like that. We are representing this control, this we are representing as a target. And in this target, we are having the X gate internally. Okay. In the C naught gate, we are having the X gate internally. So the work of the X gate is to flip from toggle from 0 to 1 or from 1 to 0. This is the purpose of the X gate. Okay. The X gate performing the not operation. So, but when to perform, it will be decided by somebody else. So this somebody else we are calling a boss, that is control. So what is the logic? Logic is that we have decided this logic, nothing, nobody else. There is no rule to decide this. We have decided it knowingly. That if control will be 0, if the control is 0, then this gate will of no use. If the control is 0, this gate will of no use. F and if the control is in one state, if the control is in a one state, then this gate will perform. This gate will perform the function. Right. So it is just like having a one boss in your office. Without that permission, you cannot perform your function. Okay. So the one example of daily life, I always used to give this daily life examples. So you can form, uh, you can take the example of remote control and a TV. This your TV unit is having the electricity plugging at here. Okay, he has a switch at here, and there is a remote. Okay, when this switch is off, means zero state, you can press multiple times on or off button of TV, but TV will not going to work it. Okay, until unless if you will switch on this button that is in one state, this toggle button will work and the TV will go on or off, or the remote will work. So this control is deciding the remote want to work or not. So at here, this control is deciding whether this X gate will perform or not. The performance of the X gate is to control the opposite, to do the opposite. So that means there are two qubits. So that means 0 and 1 combination we can apply it here. So the combination like that, 0 0 we can apply, 0 1 we can apply, 1 0 we can apply, and 1 1 also we can apply. And only we have to see one logic. This is control, this is target. Okay, we have to see if the control is 0, so this will not flip. When this will not flip, the same will come as it is, 0 0 0 1. If it will flip, the control is 1. When the control is 1, the target will work, then this 0 is converted into the 1, this 1 is converted into the 0, like that. So this will be the output. This will be the output. So this is the truth table for this C naught gate. So it's needed for the quantum computation. The application for this is entanglement. Entanglement means to say, entanglement is a very important property also. So the entanglement means to say that one of the input is connected to the other input. So at here, that's why we are giving a relation of control to target. When control is 0, there is target is no longer work. When control is 1, the target is allowed to work. So this entanglement we are given, this concept of entanglement we are given through this C naught gate. That is control and target both are not independent. They are dependent now. So the outputs are also dependent on this control and target. Okay. So yeah, David Deuce has introduced this quantum logic gates, and also he has showed that this C0 gate, Hadamard gate, and the single qubit gate. Single qubit gate means Hadamard gate also. That is forming a universal operations. Now, before moving towards the C0 truth table is very easy. No worry. Before moving it in the another gate, CC0 gate, first we will introduce like this. Suppose in the single qubit gates, we are having a 0 and 1 state only. When we are having a 0 and 1 state, so only two basic state was there, cat 0 and cat 1, right? But in the double qubit state, this just like a C naught is a double qubit state, multi-qubit state, double qubit states. There are two qubits. The qubit first, Q1, having a 0, 1, qubit 2, having a 0, 1, right? So ultimately, the number of states are now like this 0, 0. This is the one state. Another state is 0, 1. Another state is 1, 0. Another state is 1, 1. These things. So now the basic states now will become 4. Okay. So these are the basic states in the multi-qubit or double qubit gates. So in the single qubit gates, the basic states are 0 and 1. So we are representing superposition state like this. In the single qubit gate, the superposition state we want to represent like this: alpha of base state plus beta of base state. But when we are moving to the double qubit gates, so double qubit states 0, 0, 0, 1, 1, 0, 1, 1. These are the four states. Okay. So we will represent like that. We can say alpha, beta, gamma, and something else more we can represent. Or P1, P2, P3, P4, we can take it. So we can represent the superposition state at here also. P1, amplitude of 0, 0 state, plus P2, amplitudes of 0, 1 state, plus P3, amplitudes of 1, 0 state, plus P4, amplitude of 1, 1 state, like that. So this will be the superposition state of double qubit quantum gates. This is okay. So in the double qubit, the superposition state, again I am writing here because that was some dirtiness was there. So maybe some viewers will see or not clearly. So P1 is the possibility of being in 0, 0 state, plus P2, possibility of being in 0, 1 state, plus P3, possibility of being in 1, 0 state, plus P4, possibility of being in 1, 1 state. Okay. So the total possibility, the condition will remain same. In the one qubit, we are requiring the condition alpha square plus beta square 1. Here, we will remain the condition in the same pattern. P1 square plus P2 square plus P3 square plus P4 square is equal to 1. So this normalizing condition will remain same. We are going on to increase the number of qubits, but this normalizing condition will remain the same at here also, at here also. Okay. So like that. One more thing, how to evaluate this 0, 0 state. We have writing this 0, 0 state. So evaluate this state, the matrix formulation of this state, we have to perform one qubit 0, the tensor operation, the tensor multiplication of this 0. So when we will perform this 0 to 0 like this, the tensor multiplication, this is having 1, 0, then tensor product, this is having a 1 0. So what we are doing in the tensor, we are just multiplying the permutation and combination. That means this as it is, we will multiply to here. This as it is, we will multiply to here. So we will write like this 1 0 to 1 0. Sorry, this is 1 to 1 0. 0 to 1 0. In the next form, we will write like this 1 to 1, 1, 1, 1 into 0, 0, 0 into 1, 0, 0 into 0, 0. This is the tensor multiplication. And see the difference? This was in the two elements. This was in the two dimension, two elements. But this was in four. So we have diversified the dimension also here. Okay. That is a different method that it remains a column matrix. Yeah, it will remain because this is the column, this is purely a column. When both are column, it will remain as a column matrix, but we can take it as like this. Okay. Suppose for the suppose we want to evaluate 0 1 state. So 0 1 state is like this. It is a 0 tensor product of 1. When 0 tensor product of 1 we want to take it, we can take it like that. 0 means 1 0 matrix tensor product of matrix 0 1. So when we are taking a tensor product, we are taking a permutation combination. That means same thing we will multiply by this and same thing again we will multiply this. So that means we can write like this 1 0 1 0 0 1. This is. And when we are opening these things, we can open like this 1 into 0 0, 1 into 1 1, 0 into 0 0, 0 into 0 0. So this is the matrix form of cat 0 1 state. Okay. So like that, we can evaluate the matrix form of all the four states, that is 0 0, 0 1, 1 0, and 1 1. Just remember the sequence matters a lot here. That means you cannot do opposite. That is here also. Suppose you can take this as a first, this as a second. You cannot do like this. It's wrong. Okay. So here, yeah. So this is like a C not gate truth table. Now, now the another boss we are we are sitting above than the C naught. So that is called the double C naught gate, CC naught gate. Okay. So that CC naught gate is also called the Toffoli gates. So in the Toffoli gates, yeah, one thing is remaining. One minute. In C naught gate, if we want to represent the matrix for the C naught gate, so the matrix for the C naught gate, we can write it like this because we have seen there is a column matrix and coming like this 4. So that means 4 cross 4 matrix will be there. And here we will represent like this. This is 0 0 state. This is 0 1 state. The sequence matters a lot. We can form the matrix like this 1 0 state, 1 1 state. Okay. So when 0 0 state, we are having a column matrix of this one. That is 1 0 0 0. In the 0 1 state, we have said that 1 is slipped by one place. That is here. Rest of the 0 0. So when you will go by sequence, this by this, then this, then this. This will be a sequence. So when you will go by the sequence, then you will see it will place displaced one below. That is 0, 0, 1, 0. Here you will replace this 0, 0, 0, and 1 like this. But this is not the matrix for C naught. This is the matrix for original 4 states, but it is not the matrix for the C naught gate. The C naught rat matrix will include the output also. So we are seeing here the 0 0 having a no change. That means in the 0 0 state, we will have a no change. No change. In the second 0 1 state, there is a no change. So there is a no change. But see here, there is a change 1 1. And there is a 1 1 to 1 0. So there is a reverse. 1 0 changing to 1 1 and 1 1 changing to 1 0. Right. So that means this 1 1 now clearing the outputs. Yeah. So this is a 1 1. This will shift to here. And this is a 0 0. This will shift to here. That means this 1 will shift to here and this one will shift here. Okay. So that is the matrix which comprises the output of the C naught gate. So this is the matrix transformation matrix for the C naught. So in this way, we are having this transformation matrix of C naught for the mathematical computation point of view. Now, now we can move ahead to the joint family decision gate. So joint family decision gate, just like a CC naught gate. So one boss, we are also sitting. So there are two bosses now. So the same concept is there. There are two bosses now. So that means with the consent of the two bosses, this gate will work. So that means when it is one, it is one, only then this will flip. This will flip. Only then when both are one. If anyone is not in the one state, anyone is zero state, then this will not work. Anyone is the zero state, it will not work. Okay. So because there are three qubits now, first, second, and third. For the three qubits, again we will derive the same input conditions from the tensor product. So what are the input conditions? The input conditions like that. Three qubits means controls cat 0, tensor product of cat 0, and tensor product of cat 0. So this we have computed in the C naught 0 0. So this we have got the result of 0 0 like this. And 0 0 matrix we are having. So we can have the matrix like this 1 0, and this we are having the matrix of 4 cross cross like this. So this 4 cross 4 matrix multiplied by 1, we will write it here 4 cross 4 like this. Okay. And then this same 4 cross 4 matrix multiplied by 0, we will write it here. This. Okay. And the same thing we will perform at here also. At here also. So that will give you a double tensor product and will give you a full matrix of 8 cross 8. So see the pattern here. So pattern here also same. It's a diagonal. But this diagonal will come when you will follow the sequence. The sequence will be 0 0 like that 0 0 0 1 1 0 and 1 1. In the three qubit gates, the sequence will be 0 0 0. Then remains this 0. This is 0 1. This is 1 0. This is 1 1. All are having a 0. Now same thing, same consequence. Repeat with the 1. That is 1 1 1 1. Same consequence will repeat 0 0 0 1 1 0 1 1 like this. Okay. So these 8 states will be here now, 3 qubit states. When there is a 8 state, the matrix will be of 8 cross 8. Okay. So here also, when we will see the truth table of it, in the truth table, this is interchanged like this. That's why there is a sequence. Otherwise, it should come at here, it should come at here. It will form a full line. But in the output, of CC not gate only in the last input. Only in the last input that is going to change. Okay. So that is for the C not gate. Mhm. So that is uh, that is sufficient for today. So we are leaving this 5 minutes for the further discussions in the chat box. If somebody has having a doubts or somebody wants to clear something, that he can have the things in chat box. Let me see what's the questions. Is anything? No. Hmm. Yes. So I'm waiting for your questions. If anything, doubt, anything else you want to include in my upcoming sessions. The reading resources, yeah. Mm. Yeah, we will provide that resources in the LMS. We will provide to the team. The team will update in the LMS portal. Yes, reading personal references. The reading resources, there are a lot of references are there. So we will provide that. And in the last session, I will be taking research outputs. So there we will be discussing research papers in the last session also. So there I will tell you also the what are the latest resources you can use it. All gates have to be used or anyone can be used in quantum computing or as per application. Yes. Why you will use all of gate? No, there is no requirement to use all of gate. It depends on particular case to case. This thing will more clear when we will study the algorithm tomorrow. So we will be discussing different. There are three or four algorithms. We will be discussing that algorithm along with the daily life examples. So in that we have to use this quantum gates and the quantum circuits. So there are some series connections and parallel connection of that gate is remaining. So we will discuss these things in the next session, and then we will discuss also along with that we will discuss the that algorithm. So when we are designing the algorithm, we are designing the circuit for the algorithm. This thing will clear to you. So what are the applications and how, as per the application, we are going to modify that gates or sequence of the gates. Yes. Anything else? Uh, Waiting for your questions. If you want some suggestions, then you can also put the suggestions. You want something involved in the things. Yeah, feedback link you will get it. What should we do to get comfortable with the area of quantum computing and what are the topics for tomorrow so that we can read? Yeah, the topics for the tomorrow, we will discussing the series and parallel quantum circuits. We will be discussing the algorithm. We will be discussing the some of the uh, Qiskit codings, that what are the Qiskit programs that are required to create the basic circuits in the algorithm. What should we do to get comfortable with the area of quantum computing? Just comfortable. Comfortability comes from if you are feeling that this is our own subject. So the very difficult one question is that when we are entering the quantum computation subject, we are not feeling from for so much long time. For so much long time, we are not feeling that this is my own thing. Okay. Suppose you are studying coding, so you are feeling this is my brother, this is my sister, like that. This is my family member, but you are not studying feeling this quantum computation subject like that. So the thing to encounter that is to root it to you, although it will take a time, but just root yourself in the physics and mathematics. That will take you the things. Though I learned the quantum gates multiple times, but can't do it afterward. Uh, okay. Uh, we, we, we will have some thoughts on that tomorrow. I'm noting this thing. Yeah, I'm noting this thing. Yeah, there is a trick. Yeah, there is a trick. There are tricks. X, Y, Z. When you will see combinedly, na, what I think the main purpose, main thing is that you are not seeing all the quantum gates combinedly. Just on what there's a one suggestion from my side that have a chart, and in that chart have the truth table of all the gates combinedly. Then you will get to know that this gate is performing only this function. There is a one function for one gate. Just recognize that function. For the X gate, there is a function, not gate. For the Y gate, there is a function. Y gate, I will tell you later. Z gate, there is a function of adding a negative sign. For the Y gate, there is a both the functions. They are performing X and they are performing Z nature, both nature also. For the Hadamard gate, there is a no comparison. Hadamard gate at the top, and the Hadamard gate is having a superposition. It's only used to define the superposition, which is readily used in the algorithm. We will discuss about this. Yeah. Anything else? So we are winding the session. Okay. So I think that's end. So okay. So hand it over to the Sushmita.
Yeah, yeah, sure, sir. Thank you so much, sir, for your informative session. We'll meet again by tomorrow at 3 p.m. Thank you so much.
Yeah. Thanks.
Yeah, so dear faculty members, just a reminder, kindly mark your attendance. And some are asking for yesterday's attendance link. As we informed, the attendance link will be active only till 5:30. So yesterday's attendance link will not work, so which I am not able to share it. So I request not to ask the attendance link for the next day. Okay. So please mark your attendance before 5:30. Okay, yeah. We'll wind up for the day. Thank you all. Thank you for joining.